G'day viewers. In this segment I'll talk about message confidentiality using cryptography. So what we're really trying to do in this lecture is understand how to encrypt information that's sent over the network to provide confidentiality. This is the classic threat of eavesdroppers being able to read messages and spies wanting to be able to send coded messages that can't be understood. Of course, we're going to get a little more modern and think about how it's used in networks. I'm going to tell you about two different kinds of schemes that are used to provide encryption for confidentiality. And they're symmetric or secret key schemes and public key or asymmetric encryption. And as I go through this, we're going to treat the crypto functions themselves as black boxes. So this is really more about how to use some of the primitives rather than exactly what bit operations are used inside the primitives themselves. It's very interesting to understand more about the crypto primitives themselves, but to do that we'll need to go over to a security course. Okay, so one of the first things I want to talk about here is the goal and threat model, so we understand what kind of security it is that we're trying to provide. The goal here is to send a private message from Alice to Bob. So Alice can send that message across the network to Bob and it will remain private. No one in the middle, Eve, will not be able to understand the contents of the message. This is called confidentiality. And you can see I have the diagram here. Alice is sending that message to Bob. And Eve here should not be able to read the contents of the message. That's the threat we're trying to protect against. Eve here is what's called a passive adversary. That means that she just gets to observe the messages as they go to and fro. She doesn't get to inject any of her own messages or tamper with them or do anything like that. So the threat model is simply that by observing them and looking carefully, she'll be able to understand what they say. If they're just sending the plane, well, that will be pretty obvious. So we're going to have to do something about that. Here's what we'll do about it. We'll use an encryption and decryption model. So this figure here shows the general setup for encryption and decryption to provide confidentiality. Alice is here over on the left, Bob's here over on the right. Alice and Bob, by the way, are standard names in cryptographic schemes. They were invented by Ron Rivest in some of his early papers, and now they're just used all over the literature. So Alice is going to send to Bob, and the message itself is called this plain text. So here's the plain text here. I love networks, of course. What else are you going to say? Now, we can't send this plain text over the network, or Eve's job in the middle will be trivial because she'll get the message. Instead, we want to encipher it and send what's called the ciphertext. That's this scrambled message here. So what Alice will do is she will encrypt the message before sending it. And she will encrypt it using this box here, this function, which we'll look at some schemes a little bit more in a moment. Once it's encrypted into this ciphertext, Eve will see the ciphertext because she's observing all of the network messages, but she won't be able to relate it to the original message. The encryption is parameterized here by a key. Now, if Bob has the same key, he'll be able to decrypt it and get back to plain text. And under this model, we've then sent a message across the network from Alice to Bob, but Eve hasn't been able to read it. Well, let's talk about that a little more and begin to go into some of the details and look at the schemes. The picture gives you the general setup. You should realize here that the encryption operation is a reversible mapping. So the ciphertext in some sense is the plain text, it's just confused. But there's a one-to-one mapping between them that can be reversed. So we can map a plain text into any plain text into its corresponding ciphertext and any ciphertext into its corresponding plain text. We also assume here, and this typical assumption, is that the attacker knows the algorithm. This dates actually from the 1800s as a general principle, in that you don't want the security of the algorithm, of the scheme, to rely on the security of the algorithm. Because if someone leaks the details of what the algorithm is, then it's all over. Instead, what happens is the algorithm is assumed to be widely known, but it's parameterized by a key. This key is secret, so it has to be held secret. If the key is compromised, then you can use the same algorithm with a different key. And an attacker, even if they were able to break the scheme with one key, they shouldn't be able to break it with another key. Of course, the problem here is that the keys need to be distributed. In some sense, we saw previously that Alice and Bob both had a key, so some kind of key needs to be distributed. This often turns out to be the Achilles heel of encryption schemes, because you've got to be able to get the key somewhere before you can really start sending encrypted information. And that's hard, since you can't easily encrypt that key to send it, because you're bootstrapping the system. Okay, so I'm going to talk briefly about the two different kinds of encryption schemes that you'll run into, and their pros and cons. That's our job for this segment, to find out about these two kinds of encryption. And they are symmetric key encryption, or secret key encryption as it's called sometimes, and public key encryption, or asymmetric encryption as it's called sometimes. I'll go into both in detail, but in a nutshell, the difference is the way the keying and the encryption is done. In symmetric key, Alice and Bob both have the same secret key. So they're sharing a key, and it's got to be secret. If you know the key, everything's over. And encryption is really mangling the bits of a message using this key in some way, making them unrecognizable by mixing them up. An example of a symmetric encryption scheme that you might have heard of, by the way, is AES, the Advanced Encryption Standard. Okay, the second kind of encryption family, and I'll tell you a little bit more about both of these in a moment. The second kind of encryption family is what's called public key encryption. Here, the keys are different. This is really pretty funky. Everyone has a key, so Alice and Bob both have their own key, only each key is split into two parts. It's split into a public part, which can and should be widely known, so everyone can see the public part of a key. And also a corresponding private part. That private part needs to stay secret. Only the owner of the key should have this. If they lose it, it's all over. Encryption in this funny split scheme is actually based on different kinds of mathematical problems. You might have heard of one well-known public key scheme called RSA. That scheme is based on the mathematical problem of factoring. It's very difficult to factor very large numbers that are the product of two large primes. So that difficulty allows the construction of a problem that, the division of a problem into two parts. It's very easy to take the mapping one way and very hard to take it the other way. And that's going to translate into us having a key, part of which is public, part of which is secret. So let's talk about both of these schemes in just a little bit more detail so you can see what's going on. Here's the same general picture as I had before. So in symmetric key encryption or secret key encryption, Alice and Bob have the same key. I've called that here KAB, and you can see here it is. They both have it, and it's marked a secret key. They both have it, and they need to keep it secret, because anyone who possesses this key can read messages and send messages with the same cipher. And they simply go through the same motions that I've described before. They encrypt using this key. It moves from the plain text here to the ciphertext here. And on the other side, they decrypt using the same key, and Bob is able to get the plain text back. So that was symmetric key encryption. That's it. I'm not going to tell you the details of what's inside the encryption boxes, because that's really beyond what we can cover. Okay, the next one, public key encryption or asymmetric encryption. This is a little stranger. So here's our diagram again, and the key concept here, the key difference is that Alice and Bob each have their own key, and that key is split into a public-private key pair. So there are public and private portions of the key pair. I've shown here Bob's key. So we have KB, that's the public part, and KB to the -1, that's the private part. -1 there is really sort of implying the inverse operation. So now, in this scenario, Alice is going to send to Bob, so we're interested in this direction. And for the keying arrangements, Alice is going to get to use Bob's public key, that's KB, to send a message to him. And Bob is going to have his private key, that K to the -1B here. So those are the keys we have. So here's how it works. Alice is going to perform an encryption operation to get the ciphertext, but to encrypt she simply uses Bob's public key. Now actually Alice is doing this to send to Bob, but since this key is public, anyone can get it, should be able to get it. And since they can get it, anyone can encrypt a message that's sent to Bob. And when it's encrypted with this, it will be ciphertext that no one on the network, like Eve, should be able to understand the contents of. So that was the first step. The second step, as it goes over here, is that Bob decrypts it with his private key, and he can get back to plain text. Now that private key, KB to the -1, is a key that only Bob has. So he hasn't given this key to anyone else, not even Alice. So he's the only person who is able to decrypt and read this message. So we've created a system where anyone can send an encrypted message to someone and only they can read it. That's public key encryption. So one of the difficulties, the key difficulty really, with these schemes has to do with key distribution. Okay, it's a big problem, a major problem on the network. Now, if we were all just spies, and maybe it wouldn't be such a problem actually, because presumably there are a small number of spies and we have long-standing relationships and we can set up a key between us ahead of time. Maybe we needed to meet to ensure there was some trust initially. On a network, however, hosts will often want to talk to other parties who they've never met before and they have only the faintest notion of who they are. So to do that, we would always like to be setting up new keying arrangements. We can't really do that. It's problematic with symmetric key encryption. And that's because, before we can use symmetric key encryption, you need to set up a key with someone. So you sort of need to know them ahead of time to set up the key, but we're always meeting these new parties. This is where public key encryption really comes in handy. You can send a message to someone, and if their public key is available, they can publish the key on their web page. Everyone can know it. So public key encryption would seem to go a long way to help us with setting up key arrangements, because servers can publish their own public keys, and that way you can send a message to the server that no one else can read. This is great. We'll see later though that it has its own difficulties. And the difficulties really have to do with needing a trusted directory service to distribute the public keys. I mean, how do you know you have the public key for the server as opposed to someone else's public key? It's just a public key after all. So there's a problem between binding public keys and their identities. And we'll look later at how certificates are used to deal with this problem and make it a little easier to solve. These are used widely on the web, for instance. Okay, so now you know a little bit about symmetric key and public key encryption. To compare them a little more, I'm saying here really that they have complementary properties. We covered this property, key distribution. For a symmetric key scheme, it's hard because you have a key per pair of different users or hosts. There are a lot of different pairs, so there are a lot of keys, and every time you want to talk to a new person, you need to distribute these keys. With public key encryption, it's easier because you only have one key per host, not per pair of hosts, so that's a lot fewer keys. And for the host, the public portion can simply be written on a web page or made available anywhere, so we can distribute it widely. We want to do that. We want everyone to know everyone else's public key. Well, the flip side of this is this other property, runtime performance. Now, it turns out that symmetric key encryptions that mangle bits are relatively fast. These days you can encrypt with symmetric key schemes quickly enough to be able to send data at high rates over the internet, all by doing it in software. You used to have crypto boards and other kinds of hardware support, but these days even your microprocessor instruction set has a little bit of support for encryption, and you can just encrypt in software and it's usually fine. On the other hand, for public key schemes, encryption tends to be very slow. And I'm talking about orders of magnitude, maybe 3 orders of magnitude slower than symmetric key encryption. So you'll tend to want to send infrequent messages or small messages with public key cryptography. The catch here, of course, is that we want to get the best of both worlds. Public key was very useful for keying arrangements, but we really want the performance of symmetric key encryption. No one, by the way, wants to pay extra for security. We'd all like security for free. We don't want it to slow us down or inconvenience us in other ways. But it turns out that we actually can come up with a winning combination that gives us the best of both of these properties fairly well. And it works like this. If you think about it, actually, maybe you could work it out ahead of time. That would be a good exercise. But we can do this. So if Alice is trying to send confidential messages to Bob, she can begin using public key encryption. She can send a very small message to Bob. that can be a secret key. So this might be 256 bits. Once she's done this, Alice and Bob share a secret key. Yay, that's exactly what we wanted. Then Alice and Bob can switch over to symmetric encryption and use that to send many large messages very quickly, all using the shared key that we've now established. So this combination, this technique is used very frequently in practice, and this key which they generate just to use, the symmetric key, is called a session key. So a session key is typically generated and used over the short term just for a particular session. And the next time you want to do it again, you generate a fresh session key. Okay, so now we've seen how to encrypt messages for confidentiality. We've got the basics of that. We'll see how to apply that to different schemes later on.